Inflection points are where concavity changes from positive to negative or vice versa. And concavity is talking about the second derivative, whether it's positive or negative. So with both of these, we want to take a second derivative, find the second derivative. So we need the product rule here because it's two different functions of x multiplying. So it's the derivative of the first function times the second function kept the same, plus the first function kept the same times the derivative of the second function. Not sure what's going on with my words today, but second derivative now. This also needs the product rule, and this one's going to need the product rule. This is going to be a big mess, but I think your problem in your textbook is a little easier. So, sympathize with me a little bit here. Okay, derivative of the first function times the second. I'm on this one right now. Derivative of the first function times the second function kept the same, plus the first function times the second function kept the same. And then I can clean it up by combining a few like terms here. These are like terms, right? And I'll factor out an e to the x while I'm at it. So I'm left with 2 plus this is 2x plus 2x makes 4x. And I factor out that e to the x. And then I've got x squared. But I factor out that e to the x. Okay, so that's our second derivative. We're supposed to set it equal to 0. And where the second derivative equals 0, or where the second derivative fails to exist, those are potential inflection points. We have to check them. Okay, so it's factored. We want to set each factored piece equal to 0, but this first factored piece, can you plug in a value for x that would make that be true? You can't. You can get really close. You can plug in negative a billion, and e to the negative billionth power is really close to 0, but it never exactly equals 0. Okay, so this factor piece didn't give us a 0, and so we just have to set this equal to 0 to solve. And this one, I need the quadratic formula. I think the one in your text doesn't require the quadratic, so lucky you. But I'm going to do negative b plus or minus the square root of b squared minus 4 times a times, oh no, my a is 1. Did I mess everything up? No, I'm good. Times c, okay, I caught it, over 2 times a. Because a is 1, b is 4, c is 2. And then when we simplify, that's square root of 8 over 2. Okay, and this might be good practice for some of us that haven't done this a lot. The square root of 8, that's the same thing as square root of 4 times square root of 2, right? And then that square root of 4, the whole reason I factor that out is because I know what that one is. I've simplified the radical. So I'm going to divide both these terms by 2. So this is negative 2 plus or minus the square root of 2. Okay, so there's two potential inflection points. I've got to check both of them. And luckily with inflection points, we don't have to plug in the exact inflection point. We know we've got negative 2 minus square root of 2 is somewhere over here, and then negative 2 plus square root of 2 is somewhere over here. So we just want to check a value between them. So there's a nice value to check. Plug in negative 2 into the second derivative. Okay, so here's our second derivative, ugly as it is. I just need to really know the sign. Okay, I don't really have to know the number. I just need to know whether I should put positives or negatives in here, because these are the only places where it could change concavity. So if I plug in negative 2 in here, this term is going to be positive, because when you raise a value to a negative exponent, it doesn't change the sign. This is a positive term. And this is going to be positive 4 minus, this is going to be a negative 8, so that makes negative 4 plus 2. So this term in here is going to be negative. Negative times a positive makes a negative. So it's negative between all those potential inflection points. So let's see what's happening to the right and to the left of those inflection points. If I plug in something to the right, like maybe x equals 0, into the second derivative, because remember with inflection points, we're just trying to see what happens with the second derivative. If I plug in 0 in here, I've got 2 times 1, because e to the 0 power is 1. So 2 times 1 is 2. That's positive. And if I plug in something to the right, let's say x equals negative 3. Wait, no, that's not far enough. Let's just do negative 10 to be safe, because that's nice and easy to plug in. Anything to the left of this inflection point, because if one of them is negative, they'll all be negative. So if I plug in negative 10, inside here, that's going to be positive 100 minus 40, that's 60, 60 plus 2. This is positive, and then e to the negative 10 is also positive. Okay, so what we determined was that these two things I got from the quadratic formula are indeed inflection points, okay? Because it changes from positive to negative in concavity. It changes from negative to positive. It switches concavity at these places. So those are inflection points, but you've got to test them. You can't just set the second derivative equal to 0 and solve, okay? Same thing with this one. I'll use the blah, 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 also known as the quotient rule. So the derivative of the first times the second kept the same, minus the first times the derivative of the second, all over the second squared. I got to clean this up because then I got to go find the second derivative. Yucky. So this is going to be x squared plus 1 minus 2x squared, so that gives us negative x squared. Sorry about that. I had x squared minus 2x squared makes negative x squared. And then we got a plus 1 left over in the numerator. And the denominator will keep it like this. Okay. Okay, so unfortunately we need the quotient rule again because we need another second derivative. So the derivative of the top function is negative 2x times the bottom function kept the same minus the top function kept the same times the derivative of the bottom function. So this one I'll use the chain rule. The 2 comes down and multiplies. And then we multiply by the derivative of the innermost function. That's all over the bottom functions getting squared again. So don't just put 2 on top. Squaring a square, the power is multiplied, so that makes x to the fourth. So now we set that. Let's clean it up a little. Oh, I don't want to. Oh, I don't want to. It's awful. Hopefully yours for homework is algebraically a little easier. So keep that minus sign. There's not a lot of hope here. You could expand this and then multiply by negative 2. Yeah, I guess I probably should do that. Okay, so we're multiplying in parentheses times itself. That's what squaring is. So when you do that, you're going to get x to the fourth plus an x squared plus another x squared. And then plus 1 times 1 makes 1 at the end. Okay, then over here, I'm not going to multiply the parentheses to each other yet. I'll distribute all those things that are multiplying to each other. So that's 4x times all this stuff inside the parentheses. So that makes 4x to the third. Plus 4x. That's all over x squared plus 1 to the fourth. Okay, so still no, calculus is on hold right now. I'm just doing the algebra in the numerator. And then over here, I've got a minus and going to distribute. That's going to be 4x to the fifth plus 4x to the third plus another 4x to the third plus 4x all over x squared plus 1 to the fourth. And I'm going to distribute that minus sign. That's going to be a minus 8x to the third minus 4x all over quotes. Quotes because it's the same thing on the bottom, right? Oh man, I don't like it. Combining like terms now, there's nothing x to the fifth that can combine. There's nothing x to the fourth that can combine. X to the third, we got a minus 8x to the third. There's nothing that can combine there. What is there? Nothing that can combine? Yeah, I guess not. So minus that 4x squared, minus 4x, minus 2. They can't possibly ask us to try to solve that. We can find one pretty quickly algebraically. No, we can't because there's, look, you're supposed to set the second derivative equal to 0 and then solve. And wherever the derivative fails to exist, that's a potential inflection point. But can you make that denominator equal 0? This is always getting squared, so you'll never get the -1 that you need. And the numerator, I must have done something wrong, because there's no way a textbook would ask you to do this, to set this equal to 0 and solve. So let me pause the video. I'll go look and see what I missed. Okay, I found something. So this is -2x, not -2, the derivative of the top function. So that would change all this by a power of 1. And so you got -2x to the 5th minus 4x to the 5th. That makes -6x to the 5th. That's not much better. -4x to the 3rd. Subtracted by that 8x to the 3rd, that makes 12x to the 3rd. You wouldn't have this thing here. You wouldn't have this term here. And then the -2x minus 4x makes -6x. So there wouldn't be a -2 here. Okay, so that's a little bit better. I'll clean it up because you can't probably read that. But the first step to get x by itself would be to multiply both sides by x squared plus 1. So we've got -6x to the 5th minus 12x to the 3rd minus 6x. So you can factor out a -6 because everything's negative. Let's change those attitudes, make it positive. Factor out an x, and you'll get x to the 4th plus 2x plus 1. Okay, now that's solvable because that's factorable. Okay, so carve myself out some extra room over here. Well, we're trying to set this equal to 0, and I factor out the -6x, and then I can factor x to the 4th plus 2x plus 1. I need an x squared plus 1 times an x squared plus 1. Those two parentheses multiply to be this down here. After all that, though, look, you set this equal to 0 and solve, you only get imaginary solutions. So there's only one potential inflection point, x equals 0. So here's our number line. After all that algebra, we just need to test 0. We want to test a number to the left and a number to the right. And if the signs of the second derivative change, then we have an inflection point. So this is our potential changing spot. So if I plug in -1 into the second derivative, remember, we don't care about the exact number when we're testing to see whether it's an inflection point. We just care whether it's positive or negative. So if I plug -1 into the numerator, this yucky numerator I had, which is the same thing right down here, that's a negative times a negative is going to make a positive 6. And then this is negative times a negative is going to make a positive 12, so that's 18. And that's going to be a positive, so the numerator is positive, and the denominator is guaranteed to be positive because it's the 4th power. So if I plug in a -1, I get a positive number for the second derivative. So it's concave up over here. Now if I plug in +1, I've got -6 minus 12 is -18 minus another 6, so it's negative over here. So x equals 0 is indeed an inflection point.